Welcome back to the Data Center Fundamentals series. In part 1, we learned the foundations of routing on Cisco Nexus switches. We discussed routing tables, administrative distance, routing metrics, static routes, default routes, and the reason dynamic routing is needed. Now, in part 2, we are going deeper into two interior gateway protocols, OSPF and EIGRP. We will see how they discover neighbors, calculate the best path, react to network failures, and provide redundancy inside the network. Let's begin with OSPF. OSPF stands for Open Shortest Path First. It is an open standard link state routing protocol. Because it is an open standard, OSPF can operate in network containing equipment from Cisco and many other vendors. OSPF-enabled routers and layer 3 switches exchange information about their connected links. Using this information, every OSPF device builds a database representing the network topology. You can think of this database as a map of the OSPF network. After building the map, the device runs the shortest path first algorithm, also known as the SPF algorithm. This algorithm calculates the best available path toward each destination. OSPF uses cost as its routing metrics. A path with lower total cost is preferred over a path with a higher total cost. OSPF also supports a hierarchical design using areas. Area 0 is known as the backbone area. Other OSPF areas should normally connect to Area 0. This area-based design helps OSPF scale in large enterprise and data center networks. So, the important ideas are simple. OSPF builds a map of the network, calculates the shortest paths, and installs the best routes into the routing table. Now let's see how OSPF is enabled on a Cisco Nexus switch. On NX-OS, many routing protocols must first be activated as features. To enable OSPF, we use features OSPF, this command. After enabling the feature, we create an OSPF routing process. For example, router OSPF 10. The number 10 is the OSPF process ID. This number is locally significant. That means it does not need to match the OSPF process number configured on the neighboring switch. Inside the OSPF process, we can configure router ID. Router ID-ID 10.10.10.10. The router ID uniquely identifies the device inside the OSPF domain. It looks like an IPv4 address, but it does not necessarily need to be an address used for normal traffic. The most important requirement is that every OSPF router should have a unique router ID. Next, we configure the layer 3 interface. For example, interface Ethernet 1/1. No switch port. IP address 192.168.12.1/30. IP router OSPF 10 area 0.0.0.0. The no switch port command changed the interface from a layer 2 switch port into a layer 3 routed interface. The IP router OSPF command enables OSPF process 10 on this interface and place it inside area 0. After the neighboring Nexus switch is configured correctly, the two devices should begin discovering each other. Before OSPF devices can exchange their full routing information, they must first become neighbors. OSPF devices discover each other by sending hello packets. These hello packets are sent periodically through OSPF-enabled interfaces. When two devices receive compatible hello packets, they begin forming an OSPF neighbor relationship. However, several important parameters must match. For example, both devices should agree on the OSPF area ID. Their hello and dead timers should also match. Authentication setting and the OSPF network type may also need to be compatible. If these parameters do not match, the neighbor relationship may fail. We can check the OSPF neighbors using show IP OSPF neighbors. When the adjacency is working correctly, the neighbor will normally appear in the full state. The full state means that the devices have successfully exchanged their topology information and synchronized their link state databases. During the neighbor information process, you may briefly see other states. However, if the neighbor remains stuck in a state such as init, xstart, or exchange, there is probably a configuration or connectivity problem. When troubleshooting, OSPF always begin by checking the interface status, IP addressing, area ID, timers, authentication, and MTU. OSPF uses areas to improve scalability. But why are areas necessary? Remember that OSPF is a link state protocol. Each OSPF device maintains a database containing information about the network topology. When the network changes, OSPF distributes link state updates, and the devices may need to run the SPF calculation again. In a very large network, maintaining one enormous topology database could require significant CPU, memory, and network resources. OSPF areas help divide the network into smaller logical sections. Routers inside one area maintain detailed topology information about that area. They do not necessarily need every internal detail from every other area. Area 0 is the OSPF backbone. Other areas normally connect to the Area 0 through devices called Area Border Routers, or ABRs. In a small data center network, using only Area 0 may be enough. This keeps the design simple. In a larger enterprise or multi-site environments, multiple areas can reduce routing overhead and improve scalability. However, adding more areas also adds more design and troubleshooting complexity. So, we should not create OSPF areas without a real reason. The OSPF area design should match the actual size, topology, and operational requirements of the network. OSPF uses cost to choose the best route. The total OSPF cost is calculated by adding the cost of every link along the path. The router with a lower total cost is preferred. For example, imagine that a Nexus leaf switch has two possible paths toward a remote network. The first path has a total OSPF cost of 20. The second path has a total cost of 40. OSPF selects the first path because its cost is lower. But what happens when two or more paths have exactly the same cost? In that situation, the Nexus switch may install multiple routes into its routing table. This is called equal-cost multipath, or ECMP. ECMP is especially important in modern data center networks. Imagine a leaf switch connected to 4 spine switches. Each spine may provide an equal cost path toward another leaf switch. Instead of using only one spine and leaving the other paths idle, the Nexus switch can use all available equal cost paths. This provides greater bandwidth and better resiliency. Traffic flows can be distributed across the available paths. If one spine or one link fails, traffic can continue through the remaining paths. The routing protocol recalculates the available routes, while the data center fabric continues forwarding traffic. This ability to use multiple equal cost paths is one of the reasons routed spine leaf architecture scales so efficiently. Now let's move to EIGRP. EIGRP stands for Enhanced Interior Gateway Routing Protocols. It is commonly described as an advanced distance vector routing protocol. Unlike OSPF, which builds a complete link state map of the area, EIGRP uses information received from its directly connected neighbors. EIGRP uses an algorithm called the diffusing updates algorithm, or DUAL. DUAL helps EIGRP calculate the best loop-free route toward the destination. It also helps the protocol react quickly when a network path changes or fails. After EIGRP neighbors exchange their initial routing information, they normally do not repeatedly send the entire routing table. Instead, EIGRP sends partial and triggered updates when something changes. This reduces unnecessary routing traffic. EIGRP uses a composite metric. By default, the main components of the metric are bandwidth and delay. The protocol evaluates the available path and selects the route with the best metric. EIGRP is known for the fast convergence and efficient route updates. It is often found in Cisco-focused enterprise environments where the operations team is familiar with the protocol. Like OSPF, EIGRP must first be enabled as an NX-OS feature. We begin with feature EIGRP. Then we create the EIGRP routing process. For example, router EIGRP 100. In this example, 100 is the EIGRP autonomous system number. Unlike the OSPF process ID, the EIGRP autonomous system number normally needs to match between neighboring devices. We can also configure a router ID. Router-ID 10.10.10.10. Next, we enable EIGRP on the layer 3 interface. For example, interface Ethernet 1/1, no switch port, IP address 192.168.12.1/30, IP router EIGRP 100. This command enables EIGRP autonomous system 100 on the interface. If the neighboring device has compatible IP addressing and is also running EIGRP autonomous system 100, the two devices should form a neighbor relationship. We can verify the neighbors using show IP EIGRP neighbors. To see routes learned through EIGRP, we can use show IP route EIGRP. If the neighbor relationship does not appear, check the interface status, IP connectivity, EIGRP autonomous system number, and any authentication or filtering configuration. EIGRP uses two important terms when discussing routes: successor and feasible successor. The successor is the best loop-free path toward the destination. This is the route that EIGRP installs in the routing table and normally uses to forward traffic. But EIGRP may also identify another loop-free backup route. This backup route is called a feasible successor. The feasible successor is not necessarily used while the primary path is available. It remains ready as a backup. If the successor fails, EIGRP may immediately install the feasible successor into the routing table. Because the backup path has already been calculated and confirmed as a loop, free EIGRP may not need to perform a complete route calculation. This can provide very fast convergence. However, not every alternative route becomes a feasible successor. The route must meet something called the feasibility condition. The feasibility condition helps EIGRP verify that the alternative paths will not create a routing loop. So, in simple terms, the successor is the best active route. The feasible successor is a trusted loop-free backup route. This mechanism is one of EIGRP's most important advantages. OSPF can use multiple paths when they have exactly the same cost. EIGRP can also perform equal cost load balancing. But EIGRP has an additional capability. It can perform unequal cost load balancing. This means EIGRP may use multiple paths even when their metrics are different. The feature is controlled using a setting called variance. Imagine that the best EIGRP path has a metric of 100. A second loop-free path has a metric of 150. Without variance, EIGRP would normally use only the path with the metric of 100. But with the appropriate variance configuration, EIGRP may be able to install and use both paths. This can improve the utilization of available links. However, the alternative path must still satisfy EIGRP's loop prevention requirements. Unequal cost load balancing should also be used carefully. If one path is much slower or has significantly more latency than another path, sending traffic across both paths may affect application performance. It could also contribute to packets arriving out of order. So, unequal cost load balancing is a powerful feature, but it should be introduced only after considering the bandwidth, delay, and performance characteristics of each path. Now we can compare OSPF and EIGRP. So, which protocol is better? There is no universal answer. The correct choice depends on the network environment and its requirements. OSPF is an open standard link state protocol. It is widely supported by different network vendors. This makes OSPF a strong option for multi-vendor networks. OSPF also supports hierarchical scaling through areas. It builds a link state database and uses the SPF algorithm to calculate the lowest cost paths. EIGRP is an advanced distance vector protocol. It uses dual to calculate loop-free paths and can converge very quickly. EIGRP supports feasible successors and unequal cost load balancing. This makes it attractive in environments where fast failure and flexible path utilization are important. In a network containing Cisco, Juniper, Arista, and other vendors, OSPF may be the more natural choice. In a mainly Cisco-based environment, where the operations team already understands EIGRP can also be effective. The decision should not be based only on which protocol appears easier. You should consider vendor support, scalability, convergence requirements, network topology, operational experience, and troubleshooting complexity. Both protocols can provide reliable dynamic routing when they are designed and operated correctly. Let's summarize part 2. OSPF is an open standard link state routing protocol. It builds a topology database, runs the SPF algorithm, and selects paths using OSPF cost. OSPF devices must form neighbor relationships before they can exchange their complete topology information. OSPF areas help divide larger networks into more scalable sections, with Area 0 acting as the backbone. When several OSPF paths have the same cost, Nexus can use ECMP to forward traffic across multiple links. EIGRP is an advanced distance vector protocol that uses dual. It selects a successor as the base path and may maintain a feasible successor as a loop-free backup. EIGRP can also support unequal cost load balancing using variance. OSPF is often preferred in multi-vendor environments. while EIGRP may be effective in Cisco-focused networks. The best protocol is the one that matches the technical and operational requirements of the network. And that completes part 2 of Nexus Routing Basics. We have now covered OSPF and EIGRP, including their neighbors, metrics, backup paths, load balancing capabilities, and NX-OS configuration. In part 3, we will move into BGP, VRF, the control plane and data plane, and hardware forwarding on Cisco Nexus switches. These topics will help us understand how modern data center fabrics scale and forward traffic at very high speed. Subscribe to NexLayer Tech so you do not miss part 3. Thanks for watching, and I'll see you in the next video.